Good evening, everyone, and welcome to our 12th weekly problem solving session for the Physics of Nanoscale Devices NPTEL course. As always, my name is Jyotishwaran. I'm a PhD student from the Department of Electronics and Communication Engineering, IIT Roorkee. So, in terms of the regular schedule, we are down to our last session. But as I mentioned before, in addition to this, I have requested that I have one more session where I can kind of summarize the whole course and give you a quick run through of everything that I have covered in the past 12 weeks and give you pointers towards what are the parts that I think are important for your upcoming examinations. So yes, let us begin today's session. So in today's session, we shall have a discussion about strain engineered devices. So this was a topic that was supposed to have started last week. So where I was to discuss about mitigating some of the non-ideal effects or electrostatic effects in a nanoscale device using strain engineering. But well, uh, time was not on our side, so I kind of skipped that. So this particular topic today will have the part from the previous week. So this will have a portion from the previous week, which I told that I will cover today. So from the previous week. And in that, we shall be exploring the idea of isoenergy surfaces and subbands. Now, previously, we had seen the notion of subbands in quasi 2D and quasi 1D materials. Now, we shall look at the notion of subbands in a more device specific constant as to context, as to how these subbands form and how they influence the transport properties of the device. And then we shall have a brief discussion on the thermoelectric effects. In this session, I shall only be covering the Seebeck effect, and that too only one theoretical part of the Seebeck effect, because most of the questions or problems that you may get about the Seebeck effect are almost directly dependent on what was covered on thermoelectric effects in general is covered directly from the materials in the lecture slides. So I don't want to retread it again. So um, I would recommend that you go back and study those portions, and if you can understand and remember what is presented in the slides, you are more or less good to go for any questions within the limits purview of this course. So over here, I shall just give a physical intuition for the Seebeck effect, and then we shall have a very small discussion on the quantum dot devices. So essentially all of these, the thermoelectric effects and the part about quantum dot devices, we shall cover through problems and just get the idea. Okay, so we shall not be delving too much into the deeper end of things, because quantum dot devices are technically, in a way, they are the logical extension of the nanoscale devices. So here we are kind of getting rid of the notion of, so what we call quantum dot devices are what we previously considered to be 0D, or let me, zero dimension channels, and of the nanoscale devices part that we have been discussing. So again, we shall well, technically they also fall under the nanoscale devices category, but the idea is transport here becomes entirely quantum mechanical. We do not have a notion of the semi-classical transport, or technically speaking, the Landauer model does not readily extend to quantum dot devices. Like there is no ballistic transport. Yes. So I can actually say ballistic nanoscale devices. Yes. So the idea of ballistic transport does not generalize to quantum dot devices because there isn't a ballistic motion of electrons. There is just a 0D confined system. So I have electrons kind of de-exciting into the quantum dot and further de-exciting to move from the source to the drain. Although again, we shall not be looking too much about the transport properties. We shall just be looking at the basic physics of the device. So without further ado, let me begin the first portion. So when we are talking about strain engineered devices, so what are strain engineered devices? So consider the figure shown here. So these are what are known as isoenergy surfaces. So isoenergy surfaces are essentially like since I have three like the three axes giving me kx, ky, and kz, what I will tend to do is I will try to plot the points such that E of kx, comma ky, comma kz equal to a constant. So I will try to plot this in this 3D space. So once we do that, we will get a bunch of collection of points, and it can be shown that, I mean, we will be seeing that it can be shown to be a set of surfaces, and so these isoenergy surfaces will actually change when a certain amount of stress is applied to the system. So what happens as a result of this stress is that the isoenergy surfaces undergo a kind of distortion, and this distortion lifts the degeneracies between the different subbands in the system. So what does this mean? We'll see that in the first two problems that we solved today. So now, how do we apply this strain? Like, how do we apply this tensile stress, or how do we introduce this strain into the system? So remember, stress is. I think I will write it here. So when I say stress, so when I say stress, I imply so stress is supposed to be essentially force per unit area, or area, or force per unit length, depending on the dimensionality of the system. So if I have a 2D system, then any stress will be written as force per unit length. And if I have a 1D system, then it's just force. So essentially, stress is a measure of the external force applied to the system. And when I say strain, what I mean is the system's response to stress. So how does the system change itself to the stress that is introduced? The system's response to stress. So if anybody has some familiarity with basic mechanics of solids, elasticity, and all of those things, you'll be familiar with these concepts. If by chance we have any mechanical engineering students in attendance for this course, well then they'll know much more than me. So I don't like this is just cursory definitions to the applied stress. Okay, so yeah, so I should not say any strain applied to the system. Any strain, let me just correct myself quickly there. Strain is never applied. Strain is like given as a response. So any strain experienced or present in the system. So stress is applied to the system. Okay. So yeah. So now how does one do I literally catch my silicon and stretch it mechanically? Well, that does not sound very elegant, and it also doesn't seem very practical on a device where I have billions of such devices, transistors. So I cannot just mechanically stretch the thing. So how do we apply stress? So stress is applied by essentially depositing materials. So let us say I have two materials with lattice constants A and A prime. For now, I will assume that they have a cubic lattice. So when I'm depositing this on that, like essentially when I'm depositing the red material on the black material, what is bound to happen is there will be a certain stretching. So, like either the red material will stretch to match the lattices of the black material, or vice versa. Typically, the material that is being deposited will need to stretch to accommodate on the bonding sites of the substrate. So the black material is the substrate. I think I can write that here. So this is my substrate, and this is the what is this? This is my well, I'm missing out on the term, but well, this is the thing that is deposited. So yeah. So as you can see, when I have a deposition of this on the subs of the red material on the substrate, I can see that the bonds of the red material are kind of stretched out to A prime. So the strain is A prime minus A divided by A. So the strain is also typically a dimensionless quantity. So this is a dimensionless quantity because it's length by length. It has no uh, dimensions. So when I have a tensile strain, we are talking about an expansive strain wherein the system has kind of the length dimensions have increased. So in that case, this delta is going to be positive. So when I'm talking about tensile strain, I'm talking about delta. I am talking about delta being greater than 0. And when I'm talking about compressive strain, I'm talking about delta less than 0. Both of these are possible. To have a compressive strain, I will choose A prime such that it is less than A. So yeah, these are the two kinds of strains that I can have on my system. Now, how does this change the device properties? So the device properties are, to understand that, let us solve a series of problems. So this was problem 5 from the last session. This was the problem that I promised that I would cover this time around. So consider a bulk semiconductor undergoing biaxial tensile strain. So how can I imagine this? So to imagine this, what I can think of is take a very simplistically. This is, please remember that what I'm doing here need not have a physical you know realization, but conceptually speaking, you can think of what's happening in this way. So yeah, let me consider this 4 cross 4. Oops, it's too far off. Yeah, so this is kind of my, let us say the red material as shown in the previous figure is what I'm depositing. So I'm trying to illustrate how I can have a system experiencing biaxial strain. Okay, so So I'm viewing, and this is a square lattice kind of viewed at an angle. So please don't think this is a what is the thing? Non-square lattice. So this is a square lattice kind of viewed at an angle. Okay, so yeah, let us say I have this material where the lattice constants are a over here and a over here along this direction also, and this is 90 degrees. So this is a square 2D lattice, or this is just a square lattice. I'm just showing one layer of material being deposited onto the. So now this is being deposited upon. So this is deposited upon. Uh, so I perform a deposition of this. Sorry, onto a new material, which is again I shall use the same convention, and let me say this time I'm drawing a smaller lattice to kind of convey the point that is this fine? No, I need to displace these three slightly. Yes, significantly better, although it's not perfectly straight. Maybe if I can tip this over slightly to this side. Yes. So I'm not going to bother drawing the grid. I'm not going to spend too much time. Let us say the lattice constants here are again an A prime and an A prime. Here I can actually do this. Yes. So this is also A prime. And let me say A prime is greater than A. Now, if A prime is greater than A, if this material needs to superimpose itself on the black material, I know that its length and breadth needs to be stretched. So it will undergo a biaxial along the x and the y axis. So let me make the axis picture also here accurate. So I'm saying that this is x and this is y. So if I perform this kind of a deposition, I would expect definitely that the x and y lattice constants will change in the red material, and I may not expect much of a change in the depth, like the height of this, the z-axis length of this lattice. So the lattice parameter along the z-axis, I need not expect a change. So that is why this is called a biaxial strain. So strain occurring along two axes. So when I write something like, when I say biaxial, I mean that this is a strain along two axes. So biaxial strain implies this is a strain along two axes. Okay, so and what is shown here is kind of a uniaxial strain, a simplified picture. Now, how do I, estimate the effective mass? So for this, we need to take a second and remember what the effective mass is. So, oops, sorry, I needed to change the layout of that. So the layout is blank. So what is the effective mass? What is the idea of effective mass? And I mean, the effective mass is something that we have been seeing since week one. I briefly alluded to this idea back then also, so but nonetheless, let me reiterate. So if I have a particle of mass m that is interacting with, say, other particles, let us say I have several such a system of particles surrounding it. In fact, I shall do something. I will, change the color for that. Say, yes. It is in a field or, in an environment of all these red particles. Need not be in any particular order, or like order is not particularly required in this case. So I am surrounded by this. And let me say there is also on top of this another potential that is present here, externally applied potential, some V of R depending on its position. For now, I will assume that it is only this, because that way my system can be treated as a conservative system. Uh, because if the potential depended on, so this V is the potential. Oops. So V is the potential energy. And then these quantities, the red particles are all supposed to be some, you know, not external, other particles present in the system. System. Now, we use the notion of effective mass to kind of translate this system to a new situation where I kind of gloss over all of these and treat my original particle as a free particle of mass m star, where m star is the effective mass, and I say, okay, let me also do something more here. So let me say the system is a finite system. We cannot define effective masses in infinite systems. The why is not like, I will not explain why that is the case, but anybody who has some experience in statistical physics or statistical mechanics will know that if I have an infinite system, I cannot assign effective masses, or I cannot properly define effective masses. So now I kind of redefine the system as one containing no other particles and essentially a zero external potential also. So V of R vector is equal to 0. Over here it is not equal to 0. Okay, so this is what I do. And at this point, the effective mass can also be variable. It is not that the effective mass is always a constant. I can also have a variable effective mass to kind of account for all of this movement, all of this, external interactions. So this is the notion of effective mass. So m star is the effective mass. So a normal particle of bare mass m is now in the presence of some interactions and external potentials becomes a, can be equivalently treated as a free particle of effective mass m star. So, and m is typically known as the bare mass of the particle. Okay, so this is the idea of effectiveness. So whatever interactions we have, we kind of average all of them out and add its effect to the mass, which is why I can also have a negative effective mass. The situation for that is, as I told you before, consider a bubble trapped in a bottle of water. So the bubble is full of air molecules, and Earth's gravity acts upon that bubble as well. However, since it is surrounded by water molecules which are significantly, whose density is significantly higher, the bubble will actually rise inside the environment of water. Outside in the atmosphere, the gases are actually held close to the Earth by the Earth's atmosphere, which is why we have the thicker layer of atmosphere at lower altitudes, and as the altitude increases, the atmosphere gets thinner and thinner and thinner. So gravity actually attracts these gas molecules. However, when introduced into a liquid environment, I can treat that bubble as a small pocket of negative mass which moves opposed to the external gravity. So I can also have situations such as that. A similar analogy can be used to explain the dynamics of holes in materials also. So yeah, so even holes are effectively similar to bubbles present in the valence band. And since it is the absence of an electron, I can treat it as relative to the system. I can treat it as a particle of negative mass and negative charge that is traversing in the valence band. Or alternatively, I can treat it as a particle of positive mass and negative charge, which is what we do. To account for the negative mass of the hole, what we do is we kind of transfer that negative sign to the charge of the hole, and we treat it as a positively charged particle present in the valence band. And we assume that there are no other charges. Like essentially, we give a net positive charge to the valence band when we are talking about excitonic, like electron hole pairs present in semiconductors. Okay, so this is the idea. So whatever interactions I have, I kind of want to absorb it into the effective mass. Okay, so now the question is, consider a bulk semiconductor. So I am going to assume that I have a cubic sample where I will say Lx equal to Ly equal to L, oh sorry, Lz equal to L, and therefore by approximations. Okay, so I will also, so this is the first part that I assume. So the second part that I assume is um, the, yes, I'm going to treat the system as an infinite 3D well. Yes. So these are the two assumptions that I need. So yes. So before the stress is applied, so before the stress, so before the stress is applied, I can write the energy as E equals h squared by uh, n squared h squared by squared, right? I will write this as is h squared pi squared by 2m star L squared times nx squared plus ny squared plus nz squared, where kx comma y comma z is equal to nx comma y comma z into pi divided by L, because the length dimensions are all the same. Okay, so this is the energy, and this m star that I'm introducing here is, you know what, I will write this as m, and here I will mention that m is the initial effective mass. So what do I mean by this? Whatever lattice interactions, electron-electron interactions, electron-nuclear interactions, all the periodic potentials, I've kind of averaged all of that into this effective mass. Okay, so this is the initial effective mass of the electrons. All right. So now after the strain, so after the stress applied, we know that Lx comma Ly, and let me assume that the strain is symmetric along the x and the y axis, is equal to L prime, which is greater than L. So now what happens to the energy? Now the energy expression becomes this. So now the new energy E prime is going to be nx squared plus ny squared into h bar squared pi squared divided by 2m star uh, L prime whole squared plus nz squared pi squared h bar squared divided by 2m star. I'm assuming Lz is equal to L still, equal to Lz. Okay, so yes, L squared. Now since L prime is greater than L, I know this energy value becomes smaller. Like this, essentially, the energy separation becomes lesser. Now, remember over here, I can treat this whole quantity to be some new, I can essentially set this entire thing to be a new number capital N. Or let me, yes, I can write this as a new number capital N. And I can say the energy of the system is equal to, and I can call this some E naught. And I can say the whole energy of the system is some n times E naught, where n takes some particular values. Okay. Sincere apologies. Where I will say n takes particular values. We shall see more about this in the next problem. Values. However, I can't do the same over here because now there are two different energy parameters and I need to do some adjustments. So in this case, what we will end up doing is I will effectively want to represent the energy of my system like this. So what do I do? What I will do is try to change in star in a way that these energies kind of scale similarly. Okay, so how do I do that? So notice that E is proportional to 1 upon m star. Okay, so E is proportional to 1 upon m star. And I can see that the energy is a sum of three quantities here. And what I can do is essentially remember here for each component of motion, each degree of freedom that the electron has in the solid, I have one E naught coming from it. So I can actually treat E naught. So I can treat and E naught to be the average energy per degree of freedom. Degree of freedom. So essentially, I need to arrive at a new average over here. Now, how do I do that? The idea is see that E is proportional to 1 by m. Since E is proportional to 1 by m, if you can go back and look at your circuit theory and stuff like that, then you will know that for capacitances, I will write Q equal to CV, and therefore the voltage across a capacitor is proportional to the inverse of the capacitance. V is equal to Q by C. So uh, since V equal to Q by C, I will know when I'm linearly combining capacitors, the capacitance will become the harmonic mean. What I mean to say is the new effective mass 1 upon m star nu should be equal to 1 plus like sigma over all possible values m star old. I hope you can understand this. Like since E is proportional to 1 by m, this kind of a linear combination will happen. Similar case to what we have for capacitors. So similar rule to calculating effective capacitance. So since this is the case, and I know m star, so here I will be summing over x and y and z over the three possible values. So the old effective mass along the x motion, old effective mass along the y motion, and old effective mass along the yes. So I will also go here and say that the solid is the semiconductor is isotropic. Conductor is isotropic. I can assume that it's a cubic solid. So I don't have a difference between the x, y, and z axis, which is why I could have the same initial effective mass. Okay. Now, oh yeah, here I don't have to put an m star. I can, oh, no. Yeah, here I can essentially just write it as m. So the along the z-axis, my effective mass is still m, but along the x and y-axis, I have a new effective mass. Now, what that new effective mass is, I'm not calculating it right now. Let me just say the new effective mass comes out to be uh, just yes, I need a new slide. So let us say m star x equal to m star y equal to ml. So here the L stands for longitudinal. So longitudinal implies along the direction of stress. So from this, I can write the new effective mass. So 1 upon m star new will be equal to 2 divided by ml plus 1 divided by m, just from this expression. Because I'm summing over x, y, and z, along the z direction, the effective mass is still m. And along the x and y direction, I have written it to be ml. So it is going to be 1 by ml plus 1 by ml plus 1 by m, which is going to be 2 by ml plus 1 by m. So now this is the essentially the harmonic mean of of the effective mass along each direction. Now, if all these three were equal, then you will see that the new effective mass is just going to be the average of the masses. But in this case, of course, it is going to be a value that is different from both m and ml. So this is how we do the effective mass calculation. So effective masses are always harmonic means of the initial legs. So new effective masses are always harmonic means of the older effective masses. Now let us move on to the next problem. Now we are moving to a more abstract situation where we shall consider a quantum system that is defined as an infinite 3D square well. So first we need to sketch the energy level diagram of the system and list the degeneracies of this system. and estimate the effective mass of the above system. Okay, so now how do we go about doing this? So how we go about doing this is, uh, yeah. So this is a 3D infinite square well. So from that I can directly, as mentioned before, I can directly write E is equal to uh, h cross square upon 2m kx squared plus ky squared plus kz squared, wherein kx equal to, oops, I should write it as E. Oh no. Wherein I say kx equal to m pi upon L, which is equal to ky, which is equal to kz. I'm sorry, just 1 second. Yeah. So where am I? Yes. So kx equal to ky equal to kz. All right. So yeah. So yes. So from this, I know that. Oh no, just, so from this, we get the same energy expression as in the previous case. So again, let me write E naught is equal to h squared by 2m pi squared upon L squared. So this is E naught, which will imply the energy of the system is going to be E naught into nx squared plus ny squared plus nz squared. So here I have nx comma ny comma nz belongs to z plus positive integers. So it starts from 1 and keeps increasing. So let me just create a new slide here. So let us just look at the energy value. So the lowest energy value, E1, is going to be when all three values are 1. So that's going to be 3 E naught. So this corresponds to 1 comma 1 comma 1. So let me write this as nx comma ny comma nz. Okay, so my second energy level E2 is going to be, one of them can be increased to 2. So that is going to be 1 square plus 1 square plus 2 square, which is going to be 6 E naught. So this is going to be 1 comma 1 comma 2 plus 2 others. So let me just write it as plus 2 more, 2 other. The third energy level, let us do like the first 5 or 6 energy levels. E3 is going to be, I can either raise one of these to 3 and keep the other to 1, or raise two of them to 2 and keep one of them 1. So 1 square plus 1 square plus 3 squared is actually 11, and 2 square plus 1 square plus 2 squared is 9. So my third lowest or highest, third lowest energy level is going to be 2 comma 1 comma 2, and there are again two others for this. And the fourth energy level is going to be uh, E4, which is going to be 11 E naught, as I just pointed out before. So this is going to be for 1, comma 1, comma 3. And again, there are two other uh, configurations where I can achieve the same energy level. And the fifth energy level is going to be 12 E naught, where I have 2, comma 2, comma 2. And there is only one possible configuration for this, plus no other. Similarly, over here, plus no other. Okay, so and then let us say for the sixth one, we will have say I think we can have 1 comma 2 comma 3. Yes, that would be 9 plus 4 plus 1, which is 14 E naught. 9 plus 4 plus 1, so 14 E naught, which is 3 comma 2 comma 1. And over here, we are going to have 5 others, because like I can have 6 permutations including this for this configuration. I can have 321, 312, 213, 231, and then I can have 123 and 132, and all of them are distinct quantum states. So now if I were to plot the energy diagram, it is going to look something like this. I will try to make this to scale. Fair enough, I guess. So my energy value is varying from 3 to 14. So I will say it is 2, 4, then I will have 6, 8, 10, 12, not enough. So I will say I will move in steps of 3. So 3, 6, 9, 12, and 15. So this is my energy axis. So in terms of E by E naught, and then over here I will have my degeneracy. So this is my G, which I'm calling the degeneracy, which is how many energy states for each of these exist. So degeneracy, let me label it in steps of 2. I have 2, I have 4, and I have 6, because that is the largest possible value. So these are the graph ticks. Lowest energy is 3 naught, which has a degeneracy of 1. And then my next highest energy level is 6 naught, which happened to have a degeneracy of 3. So yeah, between 2 and 4. So it's going to be over here. And then I have 9 naught, which again had the same degeneracy of 3. And then I had 11 naught, so that is going to be 10 and 11. I'm kind of trisecting this segment. So 11 naught also had a degeneracy of 3. And then we had 12 naught, where the degeneracy once again dropped down to 1. And then we had 14 naught, where the degeneracy shot up all the way to 6. So this is the energy diagram of, essentially the energy and degeneracy diagram of my 3D, infinite well system. So ideally, this is how my degeneracies move as the energy levels increase. And as you can see, essentially from here you can see that the maximum degeneracy, a single set of configuration can have 6. However, let us say I have two different sets of nx, ny, nz that give me the same energy values. Like essentially that's a number theory problem. Essentially I'm asking, is there a number that can be written as a sum of three squares in two different ways. Yes, such numbers do exist, but let us not go into that right now. But this should give you an idea. And the first problem is essentially just a toy problem. The second problem is what is more important. Now, we are saying that the potential is subjected to a compressive strain along the z direction. So, what do I mean? What I mean is the following. I have my initial system, a 3D cubic well. Yeah, more or less. Okay, so and let me say these are my x, y, and z axis. So yes, so I say x, y, and z. Now what we have is a compressive strain. So now the length along the z direction. So initially I had a length of L. Let me dimension this correctly. So I have a length L over here. Although it doesn't look like it, I have another length L over here, and then let us say this length is also L. Now what we have is a new situation wherein I have my Z length, which is reduced to some L prime, where L prime is less than N. Okay, so now what happens to the system? And let me say that, yeah, okay, fine. So, all right. Again, let us draw the first six lowest energy levels. Okay. And let me say, yeah, sure, why not? Just to make the problem clearer, I will say L dash is 0.8 times N. Okay, so 20% reduction in the length. So now this part has been compressed. Okay, so now what's going to happen is, let me make a new slide, or let me rather just write the energy expression here. E is now going to be written like so. It is going to be E naught into nx squared plus ny squared plus h bar squared pi squared by 2 m l dash squared into nz squared. Now I gave you this relation, so just write it as zero point 0.8, and zero point 0.8 squared is going to be 0.64. So 1 divided by 0.64 is going to be how much? 1 divided by 0.64 is going to be, that's 1 divided by 4.4, sorry, 0.64 is going to be uh, zero point 0.4, zero point 0.4, and or let me just multiply and divide by 100. So that's 100 by 64, and that is going to be 1 point 1 point how much? 36. So 36 is a further 9 divided by 16. 9 divided by 16 is going to be Let me just pull out the calculator. My mind doesn't seem to be in the mood for calculation, so it's likely going to be 1.375. Oh, 5625, not 375. So yeah, so sure. So now this is actually going to be equal to E naught into nx squared plus ny squared plus 1.5625 nz squared. Okay. So now this will cause all kinds of problems as you are about to see. So let me now pop out a new slide. Yes. Now again, the lowest energy level is again when nx equal to ny equal to 1. So that is going to be, remember it is no longer 1, so it is going to be 3.5625 E naught. So this corresponds to 1, comma 1, comma 1. And the second lowest energy level, remember that increasing nz by 1 will actually cause a greater increase in the energy level. So nx equal to 2 and ny equal to 2 is the choice that is available to us. So that is going to become 6.5625 E naught, which corresponds to 2, comma 1, comma 1 plus one other configuration, which is essentially 1, comma 2, comma 1. And then the third lowest energy level is going to be so 5625 is going to become what? Uh, yes, it's going to be 3.125. So that is going to be. Oh wait. Oh yeah. So that is 5 plus that. Oh no. Yes. 6.25. Indeed. So then I will have 8.25 E naught, which corresponds to 1, comma 1, comma 2 and nothing else. And then the fourth highest energy level is going to be two of them may have a value of 2. Like that is the order in which we proceeded. Remember, after 112, I had 212. So now, but again, nz cannot be 2. So I will have 9.5625 E naught, which corresponds to exactly 2, comma 2, comma 1 and nothing else. And then the fifth highest energy level is going to be nz can be 2 and either of nx or ny can be 2. So that is going to be 5 plus 6.25, which is going to be 11.25 E naught. So this corresponds to 2, comma 1, comma 2 plus one other. And then finally the sixth energy level is going to be just by analogy 1, comma 1, comma 3, but the 3 has to be either in nx or ny, not in nz. So now that is going to be 9 plus 1, which is 10, plus 1.5625. So that is going to be 11.5625 E naught, which is equal to, which corresponds to 3, comma 1, comma 1 plus one other. So observe the degeneracies now. See the degeneracy here, G is equal to 1, G is equal to 2, G is again equal to 1, G is equal to 1, G is equal to 2, G is equal to 2. Now, remember the degeneracies from the previous case where the average degeneracy was, between 3 and 6. So, just to be sure, so it's going to be 1 plus 9 plus 1 plus 6. So that's 9 plus 8, 17 divided by 6. So that's almost like that's 2.33. So that is like an average degeneracy of 2.3. Whereas here, the average degeneracy is, is equal to 1. So this is like 3 ones and 3 twos. So the average degeneracy is, so average G is 1.5. And over here, for the 6 energy levels that we considered, average of G is 2.33. So introducing strain reduces degeneracy. Now, what actual impact does this have? Now, for that, I will have to draw a small diagram, or rather, I will go back to the figure here. Or you know what? I will just copy paste this thing here. So now, how do I get this figure? So I get this figure from the following expression. So I get this figure from E is equal to h squared upon 2m star into k minus kx minus kx naught squared plus ky minus ky naught squared plus kz. Uh, just give me 1 second. Yeah, kz minus kz naught squared, where kx naught, comma ky naught, comma kz naught. This gives us the conduction band. Oh no, 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 it's not this. I'm sorry, sorry, sorry. So remember that we write the energy as E minus EC. Okay, yes, yes. I'm sorry, I made a mistake. Apologies. So remember that E minus EC is approximately equal to h squared k squared upon 2m. Okay, so this is our harmonic approximation. So this is the, not harmonic, sorry, sorry. This is the free particle, free electron approximation. So for small values, for small k values. Okay, so this is the free electron approximation, or nearly free electron approximation. Okay, So because of this, I can say EC is equal to some kx naught squared is h squared, oops, h bar squared upon 2m star, which is the effective mass in the conduction band, into kx naught squared plus ky naught squared plus kz naught squared. So from this, I will get the total energy E to be h squared by 2m star kx squared minus kx naught squared plus ky squared minus ky naught squared. I'm essentially subtracting E from, like I'm writing this as E minus EC. Okay. Plus kz squared minus kz naught squared. So this, you can now see, like this, essentially, let me just quickly just factor this out for one term. So this is kx plus kx naught into kx minus kx naught. So this quantity will vanish at kx equal to plus minus kx naught. So that is what I'm seeing here on the x-axis. On the x-axis, I will form two ellipsoids, one on the positive side, one on the negative side. Similarly for the y-axis, similarly for the z-axis. So when I introduce a strain, one of these ellipsoids will change the dimension because this k value will get a different scaling. Okay. Now consider the case when there was no strain. All of these ellipsoids are equivalent, which implies an electron present here can easily scatter from one ellipsoid into another. Now remember, over here the kx value is dominant and ky and kz values are small. So this is technically an electron moving along the x direction. This corresponds to electrons moving along the y direction. This is corresponding to electrons moving along the z direction. Previously, the system was isotropic. So movement in any of these directions was equivalent. So an electron could easily scatter from x direction to y direction, or from y direction to z direction, or any other combinations. This implies the electrons don't have a preferred direction of motion. But now what have we done? We have broken that degeneracy. Since the degeneracy is lifted, since strain lifts the degeneracy, there is now a preferred direction of motion. Essentially, what I mean is, I'm not saying that one direction is preferred over the other directions, but an electron that is moving in a particular direction cannot scatter arbitrarily to another direction of motion. So what do I mean by this? I mean, so these are supposed to be your energy valleys. So these are your, constant energy points near the minima of the conduction band. So there are 6 valleys present for 100 silicon, which is a cubic lattice. The introduction of strain. So strain reduces intervalley scattering. So this is the important takeaway point here. Scattering. Okay, so this, so since my electrons can no longer randomly change direction, there is a constraint. I can actually have a more directed flow. So this in turn will technically increase mobility, which in turn will lead to better conductivity. So this is the ultimate takeaway for this whole strain engineering problem. Okay, so the next question, the third question, this is just on how to sketch the isoenergy surfaces. So now consider a system of quasi like particles moving in a quasi 2D environment. Now the confinement is present along the z direction in the form of an harmonic potential. Essentially, what I mean to say is uh, along the x and y directions, the electrons are free to move. So x comma y directions, I have free motion. Okay, and along the z direction, I have a harmonic well. So the reason I chose the harmonic well is because of this. This implies the value of E is going to be n plus half into h bar omega. So my energy is perfectly quantized, and in fact it is linearly quantized. Okay, so along the z direction, I have a harmonic well which kind of confines my electrons, because as you can see, this potential is going to look something like this. It's going to look it's going to look like so. It's going to be a parabola. Not too bad. So it's going to be a parabola. So as z tends to infinity, the potential tends to infinity, which means this is a confining potential. And just, I'm not going to go into the solutions or things like that. The wave functions are going to look like this. So the first ground state wave function is effectively a Gaussian. The first excited level will be an antisymmetric function like this. These wave functions are given by the Hermite polynomials. The solutions of this kind of a potential are well known. They are among the first non-trivial potentials to be solved analytically, you know, around the same time that quantum mechanics itself was founded. So this will have either symmetric or anti-symmetric wave functions. Okay, something that I had mentioned in the initial weeks. Yeah, I told that I will give a proof for that, but unfortunately I haven't had the time to do that. Maybe in the final session I will give some references for it for people who would like to study it. Yeah, so I'm sorry about that. All right. So now let us see how and what the isoenergy surfaces will look like. Yeah, so we are down to, as you can see, the last two questions, one for the thermoelectric effect and the other for the quantum dot devices. So E is equal to, so remember this is free motion, so there is no energy quantization here. Energy can vary continuously. So this is h bar squared upon 2m into kx squared plus ky squared, and then we have uh, plus n plus half h bar omega. So this is due to the z confinement. So first things first, I know E min is equal to h bar omega by 2. Because of confinement, I cannot have zero minimum energy. Over here, I can make kx and ky as small as possible, so I can make it 10 as close to zero as possible. Technically, even here, it cannot go all the way to zero, but for theoretical considerations, we can assume that it can go all the way to zero. Now, let us say I am looking for surfaces where E is equal to constant. Let this constant, let me call this constant some, E is equal to some E naught. So now this will give me a set of equation. So this is going to give me, which implies E naught is equal to by 2m kx squared plus ky squared plus n plus half h bar omega. Now this takes discrete values. So essentially what I can do is the following. I can calculate the integer part of E naught divided by h bar omega, the floor of this quantity. So let this be some n. Uh, yeah, sure. Let this be some n. That implies uh, E naught by h bar omega, sorry, lies between n and n plus 1. Okay, so it can be greater than half also. So, you know what? I'd rather do. Uh, oh no, this should suffice. This should actually suffice. So, yeah. Okay, and further, let me write this. Yes, let E naught. Let me write this quantity here. Omega minus the actual number itself. So this is going to be some epsilon, which varies from 0 to 1. Now, if epsilon is greater than half, then I can have small n. N can vary from 0 to, sorry, n can vary from 0 to capital N, because whatever is left, that is above half, n plus the capital N plus half will still be less than E naught. So the remainder of the energy can be occupied by this. If epsilon is less than half, that implies n belongs to 0, n minus 1. Of course, in both of these cases, n is an integer. Okay, so now I will write what I wanted to write: E minus, or rather E naught minus n plus half h bar omega. This quantity, oops, is equal to h squared upon 2m into kx squared plus ky squared. Now you can readily see that this is the equation of a circle. This is actually the equation of a circle, because this quantity for various values of n is going to be a constant, and the maximum value of n can be either n or n minus 1 depending on the ratio of E naught by h omega. Okay, so what are my iso energy surfaces going to look like? So for the smallest possible value, that is where n equal to 0, integer, uh, yeah, so I've written 0 is included here. Yeah. So for the smallest value of n here, kx and ky will have the largest value of, like, the radius of the circle is going to be the largest. So essentially, I can draw this as like so. What? No. So I can do this. Yes. So this is 1212. So yes. Yeah. So this is my kx axis. This is my ky axis, and so for the largest allowed value of smallest allowed value of, wait, I should be able to draw shapes. Can I insert shapes? Yes. Give me circles. Come on. That's an oval. Where is a circle when you need one? Yes. Oh, that's a flowchart. Uh, I guess ovals are generalized to circles. So, yeah. No, I need it to be transparent. Ah, too much effort. So you know what? We'll settle for shabby circles because it's quicker, it's dirtier, but it's also quicker. So I'm going to draw a first circle that is of kind of has its radius here. Oh God, okay, this is just a bit too shabby. Don't want to do that. Please bear with me for just 1 minute. I don't need to make it this big. I can make smaller circles also. So I will just make smaller circles. No, 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 no. Yes. Yeah, so yes, this kind of looks like a circle. And then I will have another circle concentric to that. And then similarly, I will have another bigger circle concentric to that. So it will be a sequence of concentric circles. It's going to be a sequence of concentric circles. So this is, so over here I have, for this circle I will have the maximum allowed value of n, allowed value of n, and as it moves out, so as I'm going in this direction, n decreases. So these are my isoenergy contours. But I wanted an isoenergy surface. Now, how do I do the isoenergy surface? Simple, I just plot it with respect to the n also. Now remember that n is highest as the radius is the smallest, and n is lowest as the radius is the highest. Okay, so how do I do that? Now I will just draw a 3D axis. Now you'll see that it's actually going to, life is going to be significantly easier. So how do I draw this in 3D? And I will just draw a quick and dirty x-axis. Yep. So now remember, when n can vary all the way from 0, so this is the n axis, and these are again our kx and ky axis. Okay, so when n is equal to 0 on the origin, I will have a big circle. So I will have something like this. Not quite like a circle, but I hope again that the message has gotten through. Yeah, no, I can do better than that. I seem to have gone through my. Yes. Yes. This is somewhat closer to a circle. Yes. Now, as say n equal to n goes to 1, n goes to 2, there will come a point where there is a convergence. So what I'm going to do is I'm going to, yes, this will make life easier. So I will kind of extend it from here up until there. So just, yes. Now you should be seeing the picture forming. So for the next level of n, I'm going to have another circle sharing the same center but of a slightly reduced radius. And then as I go higher, I will have another circle and then another circle and so on and so forth. So we can see that. So this is the, so this is moving to 3D. So we can now see that the isoenergy surfaces is a cone. So it has a conical isoenergy surface. If I were to plot the isoenergy surfaces for this, I will get this kind of ellipsoids, 6 ellipsoids. This is a simpler problem, so you have a cone. So you may be given, potential profiles like this and asked to plot the isoenergy surfaces. So we are down to the last 15 minutes of today's session, and yeah. So we are down to the last two problems. So problem 4 is a brief overview. So this is here we are only discussing the Seebeck effect. For the Peltier effect, please refer to the slides and follow what is given there. That should be enough for your, course purposes. So now we have a two-terminal nanoscale device. So let me go back to our old conventions for one last time. So I have the source and the drain. And I have the channel. Okay, so I have my source. Oops. I have my source, drain, and the channel. Now, instead of applying a voltage, the situation that we have is the following. So I have a temperature T1 here, and I have a temperature T2 here, and it is given that uh, drain is hotter. T2 is greater than T1. Now, what is the effect of temperature? I'm not giving any potential information. So since there is no potential information, I know that I can assume that, okay, let me say VDS is equal to 0 here also. Oops. So is equal to 0. So part A, we are just going to sketch the Fermi function. Okay. Now, if both of them have the same, temperature, I will have the same overlapping Fermi distributions. So let this be the source Fermi distribution, and let me put EF to be kind of here at the halfway point, closer to this. So this is the EF. So this graph is E and F of E. Of course, this is 1, and this is 0, and this is 0.5. Now, and blue is the source. Now, what about the drain? We have assumed that the drain is hotter. Since the drain is hotter, again, remember, since there is no voltage difference, it is going to be the same Fermi level. And since the Fermi level is the same and the temperature is different, we shall have, something like this happening. Yes. And yeah, there will be a symmetry between this and this also. So I hope you can observe / appreciate that. So this is the drain. And I hope why I drew it like this, because since the temperature is higher, the KBT value essentially becomes wider, so the electron probability will kind of start reducing significantly before the Fermi level. Okay, so in this case, what happens to the transport? Now notice that as the temperature is higher, there is a lower probability of finding electrons on the drain side and a higher probability of finding electrons below the Fermi level. And there is a higher probability of finding electrons above the Fermi level and a lower probability of finding electrons below the Fermi level for the source. So essentially, let me say, let me write the two quantities. So probability of finding electrons is higher for the source for at E greater than, sorry, E less than EF, and higher for drain at E greater than EF. So what does this mean? It means the valence band has more vacancies on the drain side, and the conduction band has more vacancies on the source side. Okay, so because below my Fermi level I have the valence band, and above my Fermi level I have the conduction band. Okay, so I hope that is clear. Okay, so now what implication does it have on the transport properties? Now electrons will drift from lower probabilities to higher probabilities, which implies there will be a valence band transport from source to drain. Essentially, if all my carriers are present in the valence band, they will move from the source to the drain. Electrons will move, if they are present in the conduction band, they will move from the drain to the source. So the idea is, let me just pop out a new slide. No. So the implication is electrons, just consider diffusion, will diffuse from S to D for E. Oh, sorry. I should have put it like this. I should say yes, I will put it like this. Electrons will diffuse. Now see the electron concentration. So over here, instead of looking at the electron like lower electron concentration, I can look at it as the whole concentration below the Fermi level. So it is higher for the drain at E less than EF, which implies, yes, I will write that first. Hotter drain implies hotter drain implies the drain is hole rich. Apologies. Like it's essentially rich in both electrons and holes, right? No. No. I'm sorry. I'm sorry. So this is hotter. So oh God, what am I doing? Yeah, I'm sorry. I was just overly confusing everything. Really sorry about that. Now just let us simply write the Landauer equation. So I is 2q upon h d of e, oops, integral d of e times fs minus fd de. So this is the expression for the current. That's it. Like, oh no, I should have the broadening term also. So let me absorb all of that and write it as m of e. Ah, so m of e times this quantity. M of e times this quantity. There is no potential difference. Now, for E less than EF, this, so Fs minus Fd, oops, Fd is positive for E less than EF, is greater than 0 for E less than EF, and Fs minus Fd is negative for E greater than EF. So this tells me that there is going to be a positive current if my energy levels are predominantly below the Fermi level, and there is going to be a negative current as a result of increasing temperature uh, if E is greater than EF. So current will move. So for E less than EF, my carriers are holes. Here the carriers are holes. And heating the drain will cause a increase in the current. Here my carriers are electrons. Are electrons. So here again the magnitude of the current is increasing, but it's increasing in the opposite direction. So this is the whole point of what is known as the Seebeck effect. So we can define a Seebeck coefficient. Again, the definition, I recommend that you, so this whole thing, this phenomena, so increasing the temperature will make this value larger and larger and larger, and therefore I will have a higher and higher current. And that is the Seebeck current, the thermoelectric current. And so this is the Seebeck effect. And the Seebeck effect is positive if the holes are the majority carriers. So that is positive for p-type materials. And it is negative for n-type materials. Essentially what this means is there will be a positive current and a reverse current, but the magnitude of current will always increase. So this positive and negative only refers to the direction of current. Okay. So this is to the direction of the thermoelectric current. Of the current always increases with the temperature. Okay. So this is the basic overview of the Seebeck effect. Additionally, there is the Peltier effect and the associated Joule heating effect. Essentially, what we can see is if I have a current flowing from source to drain, then that itself will cause a heating. And because of that heating, I may have a thermoelectric current, and depending on the channel doping, it may oppose the flowing current or aid the flowing current. So those things are present in the lecture slides. Please refer to them. The important results I will briefly refer to them in the final, like the supplementary session, where I'll kind of go through the entire syllabus quickly. So there I will write those expressions as a one spot you know reference where you can just look through all the important results. Okay. So with that, we are down to the final problem for our problem solving sessions, which is problem number 5 for this slide. So here we are looking at a quantum dot device. So what I'm saying is the energy spectrum is given by En is equal to minus 25 by n squared electron volts. Essentially, there are two implications here. So first, negative energy. Negative E implies bound electrons. Okay, so bound electrons. Because remember previously, whenever we were writing the energy values, this was essentially the kinetic energy of the electron. These were moving electrons. These were electrons moving from source to drain. However, in a quantum dot device, I am concerned with bound electrons. Okay, And number two is that this particular form of energy I took, so 1 upon n square is the energy dependence in the Bohr model. So the Bohr atomic model. Okay, so this is a very simplistic model in the Bohr atomic model. So this is essentially the same as the Rydberg energy representation. Okay, so and quantum dots can therefore be treated as artificial atoms. Okay, so vacuum energy is at 0 electron volts, meaning once this energy reaches 0, I can say that the electrons are free. So vacuum energy is essentially the free electron energy level. Okay. So now first, what is the, so here I should say the maximum ionization potential. Okay, so maximum ionization potential. So each level can put 2 electrons of opposing spins. So let us quickly solve these questions. So first question 1 here is maximum ionization potential. So for a maximum ionization potential, I will need transition from lowest energy to the vacuum level. So that implies E0 minus, or rather E1 minus E infinity. Okay, or rather, sorry, E1 going to E infinity. So the energy, therefore, delta E can be written as E infinity minus E1. So that is going to be 0 minus of minus 25 upon 1 squared. So let me just write that here for clarity's sake. So this will come out to be 25 electron volts, but we need the potential. Delta V is going to be delta E by Q, and since we are talking about electrons, this is going to come out to be 25 volts. So this is the ionization, maximum ionization potential. So if I am able to apply 25 volts across this quantum dot, I can extract every single electron that is present inside it. So this is the maximum ionization potential. Okay, yes. So then, what was the second question? Second question is, oh, I forgot to load this. Second question is, if the dot is occupied by 7 electrons, what is the value of the Fermi energy? And how will this value change if the dot contained 8 electrons? So this was a question that was also previously discussed. So let us, in any event, look at the situation. So I have the quantum dot, which is an artificial atom. So all the electrons here are bound, they are confined. Okay. So the lowest energy level is minus 25 electron volts. The next lowest energy level is 25 divided by 4, which is going to be minus 6.125 electron volts. The next lowest energy level is going to be 25 by 9, which will come out to be 2.78. So as we move higher and higher and higher, the spacing between the energy levels will reduce. 2.78 electron volts, and the fourth lowest energy level is going to be 25 by 16, which will come out to be 1.5625. So that is going to be closer still. Oops. So this is going to be 1.5625 minus 1.5625 electron volts. And since I'm talking about 8 electrons, so let me just take the fifth energy level, which is actually fairly straightforward. So that is going to be further closer. And this is going to be minus 1 electron volts. Okay. So this is the ordering of the energy levels. So this is going to be from minus 25 through minus 1. Now, initially we are told that the system has 7 electrons. And, so how do I find the Fermi energy? So the 7 electrons can be occupied, in any number of configurations. So to find the Fermi energy, I should first look at the configuration of the system at T equal to 0 Kelvin. Essentially, all the electrons are pushed to the lowest available energy states. So I can keep 2 electrons here. I can keep another 2 electrons here. I can keep furthermore 2 electrons here. And the 7th electron occupies the 4th energy level. So this is n equal to 1, 2, 3, 4, and 5. So at n equal to 4, the 7th electron is sitting. The Fermi energy is the minimum energy required for a new electron or a new particle, new fermion to be more precise, to enter the system. So there is one unoccupied level at the fourth energy level. So that would give us, this implies in this case for 7 electrons, EF is going to be minus 2.78 electron volts, where 0 is technically where the infinity is and my energy goes all the way to minus infinity. I hope you understand that. The negative Fermi energy just is it's a relative scaling. Okay, minus 2.78 electron volts with respect to the vacuum level. With respect to the vacuum level. The next question is, how will the situation change for the next electron that is being entered? Use the same definition. It is the minimum energy required for a new fermion to enter the system. Now I have 8 electrons in the system. My 8th electron has entered. Now what about the 9th electron that is entering the system? When the 9th electron needs to enter the system, it can no longer go to minus 2.78. It will go to the next energy level, which is, wait, oh no, minus 1.625. I'm sorry, not minus 2.78. I'm sorry. 1.5625. Yeah. The next energy level is going to be minus. So this is part 2A. And so in 2b, if 8 electrons are already present, the lowest energy state available is at n equal to 5, which implies EF is equal to minus 1 electron volts. Again, with respect to vacuum level. Okay, so this is the second question also solved. Now the question is, assume that the system contains 9 electrons. Now what is the quantum capacitance if 2 more electrons are introduced into the system? So remember, uh, the definition of capacitance. So Q is equal to C delta Q is equal to C delta V, which implies C, the strictest sense is dq upon dV, okay, or approximately equal to delta Q upon delta V. Okay, so this is the notion of quantum capacitance. This is the notion of capacitance in general. Okay, so now how do we go about doing this? Remember, progressively we are moving. So now we have 9 electrons in the system. So I need to draw the 6th energy level also. So the 6th energy level is going to be at 0.69 electron volts. It is going to be further closer, minus 0.69 electron volts. Okay. So now how do I find out delta Q by delta V? So first, if 9 electrons are present, then next 2 electrons are added to, so 9 electrons automatically implies I'm at n equal to 5, are added to n equal to 5 and n equal to 6, because when I add 1 electron to n equal to 5, the 5th energy level, that level is filled. So the next goes to n equal to 6. This implies delta E, that is the change in the energy, is 25 upon 25 minus 25 upon 25 plus minus 25 upon 26, which will correspond to 1 minus 1.69 electron volts. So this is the change in the energy. Now remember, delta E is actually equal to delta Q into delta V. Okay, because that is by dimensional analysis is delta Q times delta V. Okay, so since delta Q is equal to C delta V, multiply by delta Q on both sides. So delta Q squared is C times delta Q times delta V, which is equal to C times delta E. From this, we get our ultimate expression, which is C quantum, the quantum capacitance, is equal to delta Q squared divided by delta E. So delta E is given to be 1.69 electron volts. So, and delta Q is 2 electrons. Okay, it's 2 times the charge of an electron, so it is going to be 4 times E squared. So that is ultimately going to come out to be 2 divided by 1.69 volts. So I can actually, like, yeah, so this is going to be the value. You can divide and find that this capacitance will come out to be like a very small value. It will be, so yeah, this is like 2 divided by 1.69. So wait, let me just, give me 1 second. Yes, so hmm. Oh yeah. I'm sorry. Yes, I missed one small step. Yeah, I just verified the solution for a second. So yes, what we need to remember is how the average energy per charge is spreading. Okay, so when I had 9 electrons, okay, E total was going to be, yes, I had to write that also. So before doing this, E total was minus 25 into 2 plus minus 6.125 into 2 plus minus 2.78 into 2 minus, all of these minuses are in brackets, minus 1 point, sorry, plus minus 1.5625 into 2 plus uh, minus 1. Yes, it's just this. So this is going to come out to be, uh, let me just quickly calculate this. So this will come out to be 71.935 electron volts. So this was the total energy of the system, which implies the average energy per electron, which is equivalent to, so there were 9 electrons in the system. So that will come out to be, yes, 7.99 or minus, sorry, 7.99 electron volts per electron. Now, when I added 2 more electrons, this energy increased. So E total, this was initial. Yes. Now E total final comes out to be minus 71.935 minus 1.69. So this is, comes out to minus 70.425. No, not 70.425. What am I saying? Uh, sorry. Sign mistake. Yeah, this will come to 73.625. Now this divided by 11 electrons, because now there are 11 electrons present in the system. So this will be equivalent to 6.69 per electron. So this is what I need to calculate per unit charge. Okay. So delta E is now this quantity, the difference between these two, 7.99 to 6.99, which comes out to minus 1.3. Okay. So every electron on an average has lost 1.3, or rather has gained 1.3 electron volts. So this implies delta E is equal to 1.3 EV per electron. Okay, so therefore C quantum, the quantum capacitance is delta Q squared, which is twice the electron charge whole squared, into uh, 1.3 EV. So this will come out to be 4 times the electron charge divided by 1.3 volts. So this will come out to be 4 into 609 divided by 1.3. So this will come out to be 4.95. Yeah. So this will be equal to approximately, yes, this is the answer that we are supposed to get. Approximately 5 into 10 to the power minus 19 farads. So if I'm writing it in nanofarads, it's going to be 5 to 10 to the power minus 10 nanofarads. So this is a very, very small microscopic capacitance, but note that the number of electrons I added was also only just, it was equivalently small. Now, this number will become larger and larger and larger as more and more and more electrons enter the system, because as we have already been seeing, as we go higher and higher and higher, the difference between the energy levels will become lower and lower and lower. Therefore, this delta E will become more and more and more small. So because of that, as we are, increasing the number of charges, the capacitance of this, the quantum capacitance of this device will also keep varying substantially. So this is kind of how we do the calculations. So yes, this is the last problem, and with this we kind of have seen all the topics that have been covered in the 12 weeks of lectures. So with this, I will bring today's session to an end. And so with this, we have completed the 12 weeks course content. We will have one more session on Wednesday. That is the time I've requested. Hopefully, you'll get a notification for the same. And yeah, so I will see you again on Wednesday, where I will, sum up all the other, like sum up the entire course and kind of give you some important things, some important tips that, from my perspective, so that it will help you further in the exams. I hope everything that we have discussed so far in these sessions have been of some help to you in understanding the content of the course better, and, solving your assignments and so on and so forth. So yeah, I'll see you again for the final session. So with that, I will end the recording and the session itself. Thank you very much.